Hello and welcome to another example of some statistics. This time we are working through an example for the t-test of independent means. And up to this point, you can check in the playlist that we have already done the discussion. We have worked through an example by hand with a hand calculator. Now we're going to do another example, but the only difference is we're going to use a spreadsheet, in this case Excel, to act as our calculator. And the benefit of that is that we have more of a layout, a better layout of all the information. We're not necessarily going to use all the features of Excel for data analysis and so on. We want to mainly focus on illustrating how it can be used as a glorified calculator, really. So let's go ahead and do that. So the book that I'm going to use for our example is this statistics book. This might not be your prescribed book. That really doesn't matter. It's just the one I have available for this video. And we're going to look at number 19 on page 309. Let's go there. Number 19. And let's just start by reading it together. Very often these questions can be super long, and I have to not hesitate to pause the video if you have to read it again and again to get on top of what's happening in this question. That is perfectly normal. So, a study of the effects of color on easing anxiety compared anxiety test scores of participants who completed the test printed on either soft yellow paper or on harsh green paper. The scores for 5 participants who completed the test printed on yellow paper were these numbers. The scores for 4 participants who completed the test on the green paper were these numbers. Now we're not doing all of these, but the main important parts. Using the 0.05 level, we want to, they tell me it's one-tailed. That doesn't always happen. I have to figure that out. We want to see if there's a prediction of lower anxiety scores for the yellow paper. So we want to know, is yellow on average giving me lower anxiety scores? Not different, that would be two-tailed, but necessarily I want to test if it's lower. And I want to go through my hypothesis testing. So in this case, I have 2 groups of different people. So this will be independent means that I'm testing. We'll do a rough sketch and we'll leave out C because we've discussed those things in previous videos. So I've already laid out some of the information. That needs to go. Some of the information with these yellow cells. The given information, 5 participants for the yellow paper group and 4 for the green one. So my sample size for yellow is 5 and for green is 2. So first of all, we can calculate the mean, which is just the average, and Excel has some built-in functions to speed that up. I start by typing average, which I can either remember or we'll show how we can look it up in a second. Then I need to select all the cells that I want to calculate this average for. It'll add them up and divide them by the sample size, which is how we calculate this arithmetic average. Let's suppose, just to illustrate this, in case this is your first video of this kind, we can also click up here to the insert function and look up some functions. Well, I want to calculate an average. I don't know what it's called. So I type in my best description or my best guess, and I click on go. And there's some other averages as well. We can click on that first one and read the description. Returns the average, the arithmetic mean of its arguments So that is the one we want. And then I can't make this any bigger, unfortunately, but hopefully you can still see. I can then select instead of numbers individually, I can just select the range and it'll calculate the average that way. And if I double click here, I can see it's the same as before. So after a while, when you use these basic functions, they become familiar and I start to memorize them automatically. But if there's a new one or I'm not sure, I can always use this insert function, sort of helper wizard. So we have our means for the two samples. The degrees of freedom in this case is one less than each. So we'll calculate that by starting with an equal sign. One less than the sample size in each case. What's also nice with the spreadsheet is I don't have to type in everything in detail. What I have here is a calculation that takes the cell right above that, and subtracts 1. If I copy this and I paste it, and I double click on this to double check, it has done the same thing. The cell was relative to where my calculation sits, and now it's taking the cell above it to do the calculation, which is exactly what we want. Okay, so very nice, handy things there. Just using it as a more efficient, glorified calculator, I like to say. So we want to get our variance estimates. So we need to look at the deviations from the mean and as well the square deviations. So for this deviation, I calculate my score minus the mean. Now I'm going to copy this over. I don't want the mean cell to move. So I'm going to press F4 and then it puts those dollar signs next to it, indicating that it's fixed. If I want to copy a lot of them, I can copy and paste, or I can hover over this bottom right corner and drag it down. That copies the formula, and I can test a random one and see, yeah, it's taking the correct score and it has fixed the mean cell. So it didn't move that one. We can do the same thing over here, for example. If I right-click copy and paste it for these deviation scores, double-click on this, you'll see that, oh, the pink one was fixed, but that's not the mean for this sample. I need to go to the edge, drag it over, and now it's using the correct mean, still with the dollar signs, so still fixed. We enter. So we see, okay, good. Now if I go to the bottom right and copy the function down, go to random one to check, yeah, the right things moved, the right things stayed fixed. So that's good. Just escape out of that. Now I also wanted the square deviations, so I'm going to take that deviation score, Shift 6, and square it. That's to the power of 2. Copy that formula down, and I get my square deviations. I can copy this because I've done the work. I put in the formula. I want more square deviations over here. Let's double check it. Yes, it takes the cell left of it and squares that, which is perfectly good. Copy those down. And of course, perhaps you feel like I'm going too fast at certain places. Of course, you can just slow down the video, scroll back and forth. You have those options available to you, so feel free to use them. So now I have the squared deviations. So just in case I forget to mention it, I did write it down here. My null hypothesis is that the mean of these two populations, of which these are samples, the means are the same. And specifically based on the phrasing of the question, I want to test if the mean for the yellow group, which is our first group, is less than the mean for the other group. So that'll make that a one-tailed test. Sometimes the wording's different, and that'll just be testing if it's equal or not equal. Then it'll be a two-tailed test. So I do have to read carefully to make sure I set up the correct research hypothesis. All right, let's carry on. So now I want to calculate the estimate of the variance rather for each of these populations from the sample. So that will be adding the square deviations. So to add, I'm going to sum up all the square deviations. And then I'm going to divide for an unbiased estimator by n-1, but our degree of freedom is exactly that. Oops, no, I did not actually divide. I can double click here to see my formula. Go to the end. I needed to actually divide by the 4, n-1. And I can copy that over and see if it's easier to make adjustments versus retype the whole thing. You see here, oh, my square deviations, I need to move that a little bit over, shorten it by 1 cell. It is using the correct n-1 right above it. So that was a minor adjustment for this calculation. Not a big deal. But I could also have typed it in from scratch. There are these little shortcuts to add to the convenience and the efficiency to get through all these calculations. I still need to know what to do. Just like for a normal calculator, it just speeds it up that I don't have to type all the detail into my calculator every time. It's more efficient. But in no way is it really doing anything for me. So I'm still technically doing it by hand, I guess. So the total degrees of freedom will then be the sum of these two. Now I can go for a sum function, but I only have 2 of them, so I'll just do 1 plus the other one. These are all technically green cells, but I don't have to color them all. Usually my system is to color the yellow cells as input, well, the input cells colored yellow, so I can see what's the given information, where does that sit, and then all the calculation cells are usually colored green. You can color them all. You don't have to. You can use your own color coding system or nothing at all. It's just a visual aid that is worth considering. Now the pooled variance estimate is going to be a weighted average of these two variance estimates. So I will start my calculation. There's probably a function for that, but I want to be aware of the formulas. Let's actually go to the formula. This book has some formula sheets at the very beginning. Go to my independent means information. So here the pooled estimate of the population variance is given by this. So it's sort of a weighted average depending on the degrees of freedom versus the total degrees of freedom, which is essentially the sample size with an unbiased adjustment. So we're going to use this formula over here. I'm not going to try and resize it. Take a mental image of that or a picture and then put it side by side. We're going to take the first one and then multiply its degrees of freedom divided by the total. And I'm not copying this to anywhere, so I don't care about fixing any cells, plus the next variance times its degrees of freedom divided by the total. And we get our 17.99 in this case. Then I'm going to look at this again because there's so many formulas. You will very likely have a formula sheet, which sounds perfectly fair. So that was the pooled variance estimate. To get the variance of the distribution of means for each population, I have to take the pooled variance estimate and divide it by the sample size. So we'll do that over here. So I'm going to take my pooled variance estimate, divide it by the sample size. For the next sample, I'm going to take my pooled variance estimate divided by its sample size. Sample sizes might be different. So I get those two, which will be important because I'm looking at the distributions of means. In this case, the difference, but the comparison distribution is based on the distribution of means and not of individual scores. Then I'm not sure if this formula, oh, it does actually show, then the distribution that I'm looking for as my comparison distribution is the distribution of the differences of the means. And that the best variance estimate of that will be the sum of the two variances. So I'm going to add, oh no, let's put it over there. This one plus this one, which will be my variance estimate of my comparison distribution. But I, of course, want to have the standard deviation. So we're going to take the square root of that. Square root is usually a SQRT. And it says there, if you can see it, it's very small, returns the square root of a number. You can always use the insert function to search for square root. Let's maybe do that. Let's delete that. I didn't finish the formula. I want to insert a function. I don't know what it's called. I'm going to type square root because that's what I want to do. Click on go. And there's a couple of them there. Try that one. And it returns the square root. Yeah, okay, that's what I want to do. So we'll do that. Then it tells me, okay, the square root of which number? Of this one. Click on OK. And there we go. Now the alpha that they gave me, I believe was 0.05. We're going to go double check. I just want to calculate my t-score while I have the formula sheet over here. So this is the formula for my t-score, difference of the two sample means, minus really the difference of the population means, but if they are the same, that difference is going to be 0, divided by the standard deviation estimate of my comparison distribution, which is the distribution of the difference of the means. It's a mouthful. So let's calculate that. Difference of the means. Well, I'm going to have to put that in brackets. Which one minus which one? 1 minus 2. Because I want to check if 1 is less than 2. Okay. 1 minus 2. Where is the mean? Mean 1 minus mean 2. Close the bracket. Divided by my standard deviation estimate, which is over there. So there we go. So now I want to go and double check on page 309. To go double check what my alpha is. 19. Oh, it was 0.05, so that's good. All right. So we'll put in a 0.05 there. That's correct. Now my cutoff is, so I want to, right, let's rewrite this. We can also rewrite our research hypothesis. I'm doing 1 minus 2. So mu1 minus, get rid of my cursor, mu2 will then be tested against 0 as less than 0. So that means I have a left one-tailed distribution that I want to check. So let's have a little picture here. I'll just draw on the screen. Hopefully that is successful. Let's go blue. So if I picture my distribution over here, centered, it's like a bell curve, just a little thicker at the end. My bell curve can never be perfectly symmetrical. We are checking if the difference is significantly negative, so to speak. So under the assumption of my null hypothesis, 0 sits over there, and there's no difference between them. I want to know if my sample produces something extreme enough. What do we consider extreme enough? If it falls in this bottom 5%, then chances are very small that would just randomly happen, with this being the distribution actually. And it would be strong enough evidence to suggest that no, this center actually sits further to the left in the true distribution, because I just randomly found something and most of them would sit closer to the center. I've positioned this a little bit maybe visually close to the center. It's pretty far out. So my cutoff, to make this decision, I need to calculate according to the t distribution and its degrees of freedom. Let me just change back to the cursor. So we can look it up with tables in our book, but those tables are in Excel as well and more accurate. Usually the book table has the downside, it can't show that many entries. So it takes a little bit of jumps that I kind of have to fill in the gaps and guess, whereas electronically the tables can be more precise. I just need to find how am I going to do that? Well, this concerns a t-test. So let's search for t-test. Let's just move it over here so that I don't interfere with my picture, which is really on top of the screen. T-test. T-test, you're going to have to go down. So I have a whole bunch of things. Let's go t-distribution instead. That might be a better search word. These are alphabetical, so I'll go down to t-distribution. So it has a bunch here. T-distribution, cumulative, I take a score or an X value, and it returns a cumulative probability. That's not what we want. We have the probability. We want the t value that sits on that line. So we want the inverse. And there's also a two-tailed one you see there. Well, we have a one-tailed situation. So we're going to go t dot inverse. And it says there returns the left-tailed inverse of the t distribution. What is my probability? Well, it is alpha. My degrees of freedom is over here, total degrees of freedom. And we say OK. And that is our cutoff t score. Let's write that down. Let's write that down. Oop, I have angered it. I did not want to anger the pen. I lost it. It's gone. We're going to have to draw it again. These things happen. These things happen. Luckily, the drawing was not super complicated. So that is an easy fix. 0.05. So my t cutoff, negative 1.89. Where is my observed? Let's make it red. My observed t score is negative 0.4. Let's put it over here somewhere. So let's say t observed, negative 0.40 if I round it. So looking at this distribution and comparing the observed score with the cutoff, I see that that's not a very extreme score. that these samples give me. And this could very well be the true distribution, because I'm quite likely to get a score like this under this distribution. Only if the observed score was far out, making it very unlikely to just randomly get, would I start to suspect, like, maybe this isn't the correct distribution. But this is a perfectly likely set of samples I could get. So we will type that up real quick and say something like, since t, we should make this t observed. That might be better. Observed t-score. Since t observed, let's do it like this, observed is greater than, maybe some space, t cutoff, we conclude that the evidence, or let's say like this, we do not reject the null hypothesis. The evidence is not strong enough to suggest that the means are, well, more specifically, that the mean of the yellow group is less than the green. Now you can phrase it again, referring to the, what was it, anxiety? I don't remember. What was it? Let's move this. What was the question? Anxiety scores. You can phrase it again with even more reference to the question. The evidence is not strong enough to suggest that using yellow paper decreases anxiety. Let's write that down. So yes, we have sort of the mathematical, statistical language of saying these things, and it's always nice to be able to phrase it in words that the original question uses. The evidence is not strong enough to suggest that yellow paper reduces anxiety compared to green paper. So it is very important to know in the statistical framework, what are we doing, how are we making decisions, but sometimes the user or the person that has this question doesn't know the statistics. They just want to know, plain English, what's the decision here? So you have to be able to phrase it in these same words. Yellow paper is not giving me a lower anxiety score on average based on the evidence that we have. All right, that wraps up this example. These take time, but it's important initially to work through it by hand and be aware of all the formulas, whether you use a hand calculator or a more efficient calculator with a spreadsheet. It's still the same, roughly the same practice that we're getting.